is a polar covalent bond? Polar covalent bonds are formed when the attraction of the atoms for the pair of bonding electrons is different. Delta positive and delta negative notation can be used to indicate the partial charges on the atoms, which give rise to a dipole. So if we look at a hydrogen bromide molecule, hydrogen has the electronegativity 2.2, bromine has the electronegativity 3.0. So therefore, bromine has a stronger pull for the pair of bonding electrons, so that will sit closer to its nucleus. Because it's electron rich, it's going to be a delta negative, and therefore the hydrogen is going to be delta positive. Permanent dipole to permanent dipole interactions can be annotated as PD to PD. The element with a higher electronegativity holds the shared pair of electrons closer to its nucleus. Remember, this is annotated as delta negative. And this causes a permanent dipole within the molecule. A permanent dipole interaction is the attraction between the two molecules, which each have one permanent dipole each. And this is known as the permanent dipole interaction. Remember, the electrons which hold the atoms together is the covalent bond. The interaction between the molecules is known as permanent dipole. So the SQA definition for permanent dipole interactions is that a permanent dipole interaction are additional electrostatic forces of attraction between polar molecules. Hydrogen bonds are forces found between molecules that have a hydrogen atom directly bonded to a nitrogen, oxygen or fluorine, also known as NOF. This hydrogen is attracted to the NO or F of another molecule. These interactions are stronger than permanent dipole interactions. These still exist, but because the hydrogen bonds are stronger, these are the forces that are going to have to be overcome to change the state of matter. What we can see here is that the hydrogen bond comes from the hydrogen atom to the NO or F, in this example it's fluorine, of another molecule. So there are three types of intermolecular force, or van der Waals force, that we have to know, and we're asked often to compare these intermolecular forces. The weakest we have is the London dispersal forces, which are forces of attraction that can operate between all atoms and molecules due to the movement of electrons. We then have permanent dipole interactions, which are found only in polar molecules. And then the strongest is hydrogen bonds, which are forces found between the molecules which have a hydrogen directly bonded to an NO or F. Remember, this hydrogen is attracted to the NO or F of another molecule. So let's have a go at comparing non-polar and polar molecules. Hydrogen chloride and fluorine are both gases at room temperature. Explain fully in terms of the structure and bonding, which has a higher boiling point. So the first thing that we always have to do is we have to put the electronegativity values from the data booklet in. So hydrogen has an electronegativity of 2.2, chlorine has 3.2 and fluorine has 4.0. So we'll start with a hydrogen chloride. We can see that there is a difference in electronegativity, so therefore we're going to have a polar molecule. We know that all molecules have London dispersal forces, and this, because of the difference in electronegativity, also has permanent dipole interactions. If we look at fluorine, there is no difference in electronegativity, so therefore is non-polar, and will only have London dispersal forces. Now, because hydrogen chloride has permanent dipole interactions, and this is a stronger intermolecular force, this means that there will be more energy required to break these, so therefore the higher boiling point. When we compare polar and polar molecules, all polar molecules have permanent dipole interactions, and they also have LDFs. So the first thing we have to say is that if the molecule has hydrogen bonds, we have to count how many, and the one with the most has the higher melting point or boiling point. However, if we're comparing two different polar molecules that do not have hydrogen bonding, we always have to default to quantifying the electrons in the LDFs. Hydrogen chloride and hydrogen fluoride are both gases at room temperature. Explain fully in terms of structure and bonding, which has the higher boiling point. put the electronegativity values from the data book. Hydrogen's got 2.2, chlorine's got 3.2, and fluorine has got 4.0. Hydrogen chloride has a difference in electronegativity, so it's going to be polar. It will have LDFs and permanent dipole interactions. Hydrogen fluoride has a difference in electronegativity. It's going to be polar, so therefore would have LDFs and permanent dipole. But also what we can see is that the hydrogen is directly bonded to an F of the NO or F, so therefore it would also have a hydrogen bond. And since hydrogen fluoride has hydrogen bonds, and this is the strongest of the intermolecular forces, this means it will require more energy to break these, so a higher boiling point. Hydrogen chloride and hydrogen bromide are both gases at room temperature, explained fully in terms of the structure and bonding, which has the higher boiling point. So firstly, we need to put the electronegativities. Hydrogen's 2.2, chlorine's 3.2, and bromine's 3.0. For hydrogen chloride, there's a difference in electronegativity, so therefore it's polar. It's going to have London dispersive forces and permanent dipole interactions. Hydrogen bromide, again, also has a difference in electronegativity, so therefore would be polar and have LDFs and permanent dipole interactions. Now, because we can't quantify the strength of the permanent dipole, we need to default back to the London dispersive forces, so we're going to quantify the electrons. For hydrogen chloride, it's got 1 electron for the hydrogen atom times 1 gives me 1 electron, 17 electrons for the chlorine atom times 1 atom, which gives me 17 electrons, so the total number of electrons for the hydrogen chloride is 18 electrons. For the hydrogen bromide, hydrogen has 1 electron for 1 atom, which gives us 1 electron. A bromine atom has 35 electrons per 1 atom, which gives us 35 electrons, which in total gives us a total of 36 electrons. And because hydrogen bromide has more electrons, it's going to have more LDF, so therefore more energy required to break these, so the higher boiling point. Explain fully in terms of structure and bonding, which has a higher boiling point, ammonia or water. So first thing we always have to do is electronegativity. So let's look at ammonia. Hydrogen's got an electronegativity of 2.2, nitrogen is 3.0, so therefore it's going to be polar, and it's going to have London dispersive forces, permanent dipole, and hydrogen bonds. It's got hydrogen bonds because there is a hydrogen directly attached to the nitrogen of the NO or F as our options. Because we've got 3 different hydrogens attached to the nitrogen, it can exhibit 3 amounts of hydrogen bonds between other molecules. If we were to look at water, we do the same thing. Hydrogen's electronegativity is 2.2, oxygen is 3.4, therefore it's going to be polar. It's going to have LDFs, permanent dipole, and hydrogen bonds, but this time it's only going to have 2 amounts of hydrogen bonds. Because of this, ammonia has a higher melting point and boiling point, and this is because it's got more hydrogen bond than water, and therefore it will take more energy to break these intermolecular forces. Higher 2016, multiple choice 2. Which line in the table is correct for the polar covalent bond in hydrogen chlorides? So if we look up the electronegativity values, hydrogen is 2.2 and chlorine is 3.2. That means that chlorine has the stronger electronegativity, so it's got a stronger pull for the bonding electrons, and therefore would be delta negative, which would mean that the hydrogen is delta positive. Because of that, the pair of electrons would sit closer to the nucleus of the chlorine atom in the bond, and therefore the correct answer to this is multiple choice answer A. This past paper questions from the Higher 2022 written 1C part 2. The table shows the boiling points of hydrogen chloride, hydrogen bromide and hydrogen iodide. Explain fully why the boiling point increases from hydrogen chloride to hydrogen iodide. So firstly, we write out the formula for each of them and we put the electronegativity values. We can see that they all have a difference in electronegativity, so therefore they're all going to be polar and have LDFs and permanent dipole interaction. Remember, we can't quantify the permanent dipole, so therefore we have to default back to quantifying the number of electrons that each molecule has. Hydrogen chloride has a total of 18 electrons, hydrogen bromide 36 electrons, and hydrogen iodide 54 electrons. And therefore, hydrogen iodide has a higher boiling point, and that's because it has more electrons, so therefore more LDFs, and therefore more energy required to break these. Higher 2022, written 1C part 1. Hydrogen fluoride HF has the highest boiling point of the hydrogen halides. State the name of the strongest type of intermolecular force found between the hydrogen fluoride molecules and explain how this type of intermolecular force arises. So when we take the molecule, we can see that it has a difference in electronegativity, so therefore will be polar and have London dispersal forces, permanent dipole interactions, but also it has a hydrogen bond. Now remember, hydrogen bonds are forces of attraction found between molecules that have a hydrogen atom directly bonded to an N or F. This hydrogen is attracted to the N, O or F of another molecule. Higher 2023, multiple choice 2. In which of the following compounds would hydrogen bonding not occur? Remember, hydrogen bonds are forces of attraction found between molecules that have a hydrogen atom directly bonded to an N or F. So what we can see in these examples here, the only one which does not have a hydrogen directly attached to an N, O or F is multiple choice answer D.